Hi, Victoria Alvin. I'm the General Manager for Building Technology and Technical Services with Kingspan Insulation. Today, we're going to be talking to you about managing moisture and condensation in Kiwi homes and a little bit of commercial as well. We will record this presentation. It will come out to you. For those that have registered and might be missing us today, thanks for joining us, and let's get kicked in. Condensation in your home can be obvious. It can be water droplets forming on a window or dripping from factory roofs, or it can occur in less visible spaces within the building fabric. Now, that can cause the decay of materials, threatening the structure of the building. Sometimes our building code regulations do not target the condensation effectively. They address other requirements around the building, and some they do well and some they do less well. So often we need to be designing above and beyond the building code to create a truly effective building. Today, we're going to be talking about moisture with the building. We're going to talk about how we can improve some of those durability issues. So some of the key areas in the home where the moisture comes from are the ground moisture and the occupant behavior. Concrete slabs are inherently porous material. They can absorb moisture from the ground and from other sources, and that moisture can lead to various issues, including mold growth, mildew, structural damage. We also have hydrostatic pressure from standing water that can physically force liquid water through cracks and joins in concrete. Now, to mitigate these moisture issues, proper drainage, curing methods, and the use of waterproofing barriers such as damp-proof membranes or tanking is useful or essential. So the damp-proof membranes, you see here, this is orange thermothene, which is our thicker damp-proof membrane used for commercial sites, a little bit more robust than the black, which is commonly used for residential. These are applied under the concrete slab. They're lapped at 150 mil, and all tapes are joined. All laps are joined to prevent any water vapor or moisture coming through the laps of the DPM. Equally, under a standing suspended floor, we might have standing groundwater. And so in those issues, we might lay a DPM actually literally on the ground underneath the suspended floor to prevent that ground moisture coming through underneath the suspended floor. When we have applications with high water tables or hydrostatic pressure, a DPM is often replaced by a tanking membrane. As a very rough guideline, if we're 3 concrete blocks or more high, we are no longer in a damp-proof membrane territory. We're starting to enter a tanking membrane territory, and an engineer will advise on there looking at the hydrostatic reports, groundwater, and so on for the build. I've included a link on the bottom there from the Eco Design Advisor talking about the use of damp-proof membranes. As always, all these links will be in the back of the presentation for you to read at a later date. The other key factor that we need to look in terms of moisture generation in the building is actually the internal behavior, or the behavior of the occupants in that internal environment. And kitchen and bathroom activities are the most. Now, as an adult, I will breathe out 0.1 of a litre, 100 mils of water vapor per hour. So that typically means when I sleep at night, I'm breathing out 800 mils of water vapor per night. Now, if there's 2 of me, that means I'm doing 1.6 mils, 1.6 litres of water vapor per night. That's actually an incredible amount. Sorry, 160 mils. I'm getting all confused now because I got flustered at the beginning. I beg your pardon. So we can breathe out a lot of water vapor at night, and that can be what causes the condensation on our windows in the morning, where we've got the cold outside and the warm inside and lots of water vapor. Our 10-minute shower might also produce 1.7 kilos of water vapor. So the key thing that we can do to control the occupant generated moisture is to ventilate our homes. Now, that just simply means open the windows in your house several times a day for 15 minutes at a time. Use your bathroom extraction fans. Do leave them on after the shower as well. Make sure all that moisture is taken out of the air before you close up the house and go for work in the morning. Use your range hood fans. Use lids on the pots to prevent all that moisture entering your living space, your furniture, your carpet, your jib, and so on. We're aiming for 0.55 air changes per hour. That's the World Health Organization for a healthy home. We're going to talk later in this presentation about how that impacts the probability of roof condensation. Do not dry your clothes inside on a rack. Do not use an unventilated clothing dryer. They will actually just pump moisture into your home. Fix leaks and avoid overwatering of plants. Now here where we run the Kingspan technical line, we'll get a couple of queries a year about a batch that's gone moldy. And that's a typical example of this. The occupants in the batch will do all their showering and laundering and so on. They'll put all the sheets on a nice little rack to dry in the sunshine so they're ready to make the beds when they come back. They'll water the plants and then they'll lock up the batch tight. And it will just quite simply grow mold within that nice warm environment, making it, an unpleasant place to return to because it's too moist inside. So let's talk about how we manage moisture in the roof design, because that's going to be critical to many of us when we're building a cold roof design. Now, the majority of our homes in New Zealand are this cold roof design. So we have the structure, the truss roof in this diagram here is outside of the insulated envelope. Here, the insulation is sitting at ceiling level. So that structure can create what's called thermal bridging, a pathway for cold to enter the building, for heat to escape the building. And we expect this roof to get condensation on the underside of the roof, sometimes on the underlays, sometimes on the structure itself. So we expect it to get wet and to get dry. That's the continual cycle of these types of roof. Now, they're very much affected by air control. So if we have poor ventilation in these roofs, they just quite simply don't function. If we have too much moisture from our occupant behavior, they really struggle to clear that moisture out of the roof space. If they don't get sun on them during the day, a cold roof really does not work. It needs to get sun on it to be able to heat it up and allow any condensation to return to a gaseous state and be taken out of the roof by ventilation. So dry air coming in and taking that moist air in the roof space out. They're also very affected by something called radiative cooling at night. Now, we know that the majority of our houses have shifted from concrete tile roofs, and I think we could call those quite vapor open, those of you who have had a concrete tile roof, to a long run metal roof or metal tile roof, which are definitely not as vapor open as a concrete tile. So these long run metal roofs are very susceptible to night sky radiation. That's when the metal roof will cool down at night significantly. It will drop below the ambient air temperature. It's a conductive material, and you might have a low pitched roof. Remember, these metal roofs can go down to 3 degrees. There's a lot of roof space facing the night sky. So that roof will get colder and colder, and we end up with condensation forming on it as the warm air basically can't hold its level of moisture in the proximity of that cold metal, and it drops its condensation. Now, you're very familiar with this in terms of dew on your car in the morning, where your car will be wet with dew, but the ground around it is dry. It's that same conversation, but it's happening in a roof every night. The more windless condition, the more open it is to the sky, the colder that roof will get. And it can also occur during the day in winter as well. The amount of moisture that forms on the underside of the roof can be directly related to basically how much moisture is in that roof cavity. Let me try and bring it to life for you like this. When we have, as an example, 25 grams of water vapor per cubic meter at 25 degrees, we might be at, say, 100% relative humidity. If I cool that air to 15 degrees Celsius, the air can't hold 25 grams anymore. It can only hold 13 grams of water. So warm air is able to hold more water vapor than cold air. So at 15 degrees Celsius, I've now got 12 extra grams of water per cubic meter. That just is now a liquid state. And where does it go? Because it's not going to be suspended in the air. It looks for the next cold surface to condensate on. And in this case, this will be the underside of the roof, as you see here. So we've got that condensation forming there. Now, of course, these numbers change according to the humidity, the dew point of your area, and so on. But it gives you a good idea about the difference between warm air and cold air and moisture holding capacity. When we think about it in terms of our internal environment is warmer, and now we've insulated our home, so we've got warmer air able to hold more moisture from our occupant activity. As that warm air rises through the jib and the vapor open insulation in the ceiling, it cools and it's no longer able to hold as much moisture. And that's where we get that change. Now that change is an effect that's come in from more insulation in our building. So we're looking to manage that. We sometimes see condensation forming on the underside of the underlay. Now, I know we're going to talk about what an underlay does in a moment, but you can see here the mechanics of condensation. We've got the condensation on the upper side of the roofing material. We know that that's the dew that normally forms on cold things at night, like our car. We've got condensation underneath the crest of the roofing profile. We understand that as well. But now we've got condensation on the underside of the underlay. Why is that? Well, it's not that the underlay is not doing its job. It's the fact that that warm air within the roof cavity is looking for the coldest area to condensate on. And at that particular point where the underlay is directly under the crest of the profile, the underlay is the same temperature as the roofing material, so it condensates there. So that's how we get condensation on the underside of an underlay. The amount depends on how much moisture is in that roof space. So you might be saying, well, hold on, I'm pretty sure that's the water coming through the underlay from the condensation. Let me help you understand why it's not going to be like that. The roof underlay is there to collect and absorb condensation and hold it until the ventilation pathway is activated in the roof. Until the sun hits it, it's able to evaporate that liquid water back into a gaseous state, and then it can be taken out through ventilation. The underlay is actually water vapor permeable. The water vapor molecule is the smaller side, 0.274 nanometers. And so it is able to pass through the underlay. So we can get moisture in the roof, water vapor passing through the underlay into the crest of the profile and being taken out. It will not allow a liquid water molecule to come through it. So it will hold out the condensation that forms directly under the roof. And it's an air barrier as well. That's because a liquid water molecule and an air barrier molecule are larger than a water vapor molecule. Now, we do a lot of testing for our underlays. Now, Kingspan Thermocraft manufacture our own underlays here in New Zealand, and we have our own in-house testing laboratory in New Zealand. So every single batch of underlays that we manufacture is, of course, quality controlled and run through our laboratory testing and to ensure it meets the standards of 2295. Now, for a roof underlay, it has to absorb 150 grams of moisture per square meter. For a wall, it's 100 grams. It needs to hold out 100 mils of water for 24 hours. That's the condensation that forms underneath the roofing material for 24 hours for a roof, but for a wall underlay, it's only 20 mils for 24 hours. And then there's vapor resistance standards and there's air barrier standards as well. So when we do these tests in our lab, this is a classic head of water test. You can see the column on the right has got dyed water and it's 100 mils, so 10 centimeters of water. That's a lot of moisture. And we've got a piece of the underlay sitting underneath that column, and we're waiting to see if any of the moisture, any of the water is going to be able to pass through the underlay. So you can see on the bottom here, we have a pass in the green box that no dye is showing on the underside of the underlay. And we have on the right-hand side, we have where some dye showed. So that failed. So that underlay batch is now removed and it's recycled into SaveBoard, where we have a circular economy within the New Zealand built environment for our products, or we can recycle it through other methods back into recycled plastic and so on. But every underlay goes through this, and that's how we can be confident it's able to hold out condensation until that activation of the cold roof system, heat and ventilation. It might take several days in winter for some roofs to get through that system, which is why we hold out so much water for so long. The moisture in the roof space can come from several different things. We've already talked about the internal management, occupant behavior, ventilation and living spaces, and the effect that has on the roof space. The air ceiling leakage, are those lights capped, or are they just simply an open pathway into the ceiling space? Older bathrooms are a typical candidate, like a chimney for water vapor in the bathroom to go straight into the ceiling space. But we might also be talking about the humidity or the climate region. Is it a low wind zone or a high wind zone? And in previous webinars, we've talked about the change in our construction environment, where we've gone from almost 800 square meter sections to a median size of 500 square meters. With houses much closer together, we don't get the same wind around a property, therefore we don't get the same ventilation through the roof. So these are things to consider in our design. Site shading or orientation are critical. Can you get sun on that roof? Now, in the image on the bottom right of this slide, you'll see there's sun on one side of the roof and it's still heavily frosted on the other. On the frosted side, that roof will be wet and cold underneath. The other side starting to warm up and start to do its activation. So we can get two different behaviors in the same roof structure depending on where the sun hits it. The roof pitch, the steeper the roof, the better the ventilation. The lower the pitch roof, the more roof to the night sky, the colder it will get at night. If it's a darker roof, it will heat up more quickly. And we have new building materials still releasing moisture. That's a comment we'll talk about in a moment. So we need to understand, is my cold roof design going to work within the parameters of my project? And we need to analyze this before we put a cold roof design in. This particular example is from Build 180. It refers to a school roof in Dunedin that was designed in a cold roof design, and I'm afraid to say it was an abject failure. And it failed because it didn't follow the principles of what is required for a successful cold roof design. You can see there those yellow lines on the image, 1st of September, 1st of May, 1st of August. Those are the months where the sun does not hit the roof in the red circle. So we're not getting sun on that roof for the coldest months of the year, which means it can't heat up, return that moisture to a gaseous state and ventilate it out. It's also a very low pitch roof. It's in a very cold climate with an average of below 15 degrees in winter daytime, very clear nights, cool temperatures. It quite simply couldn't activate the drying cycle. And then we add in the factor of the internal environment. It's a schoolroom. It's got 30 kids in there and they're all breathing out moisture for the day. I think we worked this out yesterday when we were looking at this, and we were saying if I've got 30 kids and a teacher just breathing, that could produce 15 litres of water vapor per 5-hour school day. That's an incredible amount of water vapor that would be rising up into this roof and needs to be ventilated out if it's not checked. Now, we could do mechanical ventilation. There could have been a vapor controller that would help check that internal water vapor, but it still won't fix the lack of solar lines, the lack of sun hitting the roof. They could have looked at passive vents that could be as risky as forced ventilation because they can carry a high condensation risk in a colder climate. Quite simply, Brand's conclusion for this article was that this roof would be better designed as a warm roof, which didn't have a ventilation pathway through it, but simply the dew point was pushed to the outside of the roof. So understanding when a cold roof is perfect and when a warm roof is perfect is critical to successful design. We also look at condensation during construction. We can find buildings that get a lot of condensation in them and no one's even living in them. So it's not internal occupant moisture. What is it? Well, the building materials release a lot of moisture during construction, sometimes for up to 2 years. Your typical concrete slab dries at 25 millimeters per month and releases 1,000 litres of water during its drying cycle. Paint is almost half as much in terms of solvent or water that needs to evaporate off to allow the paint to dry. And typically, our building is closed up at night, no windows are open, there's no ventilation through it, and the products are still drying and they simply collate in the building, creating condensation issues. We had a classic example here, and this is a commercial project, which you can see in the diagram or the picture on the right. It's actually raining on one side of the roof, not the other side, just on one side of the roof it's raining. And you can see in the image on the left, there's actually ice particles on the floor. So we went, what is happening in this building? And started to become insulation detectives here. Well, firstly, what we did was we got the plans and we saw that actually the cold side of the roof was out of the sun lines. So it wasn't getting any sun on it. It was becoming very, very cold at night to the point that the internal moisture in the building was freezing in the roof and then drying out and dripping during the day. You can see it's got a massive concrete floor. You can see plaster in there as well. What you can't see was that they used profiled foam closures to block off the crests in the metal profile, preventing any moisture moving up the roof profile above the underlay. And the underlay wasn't terminated or slit at the ridge, so no moisture is able to escape through the ridge of the profile. So a lot of moisture generation in the building, no way for it to get out, and it's quite simply raining in the build. In this instance, they couldn't jib until it dried out, so really they would have had to get the HVAC system going and operational so they could continue doing what they needed to do to fit out internally. Just a function of the way the building was designed and solar lines. So we've talked about ventilation within the house area. And this article from Brands talking about Skillion roof design in Central Otago measured on the left-hand diagram, it measured how much ventilation within the room will impact the likelihood of roof condensation. So you can see here, what they said is on the left-hand side of that diagram, the one with the little red circle on it, we've got a low level of internal air changes within the room and a high risk of condensation probability. By the time we get to the World Health Organization, 0.55 air changes per hour, we're starting to even out and reduce that risk of condensation forming in the roof. And on the right-hand side of that diagram, we're sitting at just over 1 full air change per hour, and you can see the risk is greatly reduced. That would be a mechanically ventilated house, as we might use under a warm roof construction, passive house, and so on. In the diagram on the right, they said, okay, well, we've reached that optimum state of 0.55 air changes per hour. We've opened our windows, or whatever we've done. And now how many air changes do I need to get in the roof to reduce the condensation probability? And again, on the left-hand side, you can see less than 20 air changes per hour in the roof. You've got just about a 0.43 probability of condensation. By the time you get to 30 to 40 air changes, you're hitting a sweet spot between how much air is going into that roof, bringing dry air in and taking moisture air out. Now, we also saw this in a great example that Brands built in their testing lab, where they took a typical gabled house and they did testing with wind speeds, and they sealed the vents in the roof and they opened the vents in the roof, and they measured how much time that roof was going to stay in a condensation condition, i.e. how often is it going to be wet. So even at very low wind speeds, we can see that a sealed house, this is in the red box there for Auckland, in the lower quartile of wind speed, in summer, when the vents are sealed, that roof is going to be in a condensation condition, i.e. wet, almost half the time, 47%. And in winter, it's almost 70%, 69% of the time. Open the vents and get ventilation through it, and it drops to 1% in summer and 6% in winter. Now, that's in the very low wind speed. And we've already said the lower the wind speed, the harder it is for a roof to ventilate. So by the time, even when we get up to 75% in Auckland, in winter, if the vents are sealed, it's 20% of the time in condensation, and it's 6% if it's open for the vents. So ventilation really does matter and is important. How much ventilation? Well, this is such an open question because it's not specific in our building code. So we're relying on the British standard, BS 5250, the Canadian standard, the Australian standard, that all talk very similarly about ventilation. There's plenty of products in the market that will talk more specifically. So I'm going to talk generally here and not be specific about any particular brand of product. But you will see that I need air to come in at the eaves of a roof, and I need that in general to be 2/3 of the air to be entering in the eaves. Now, that could be an over fascia, under fascia, soffit vent. It doesn't really matter. It just needs to bring that dry air in. And then that air is going to go out at the ridge. So 1/3 out at the ridge, 2/3 in at the eaves. That creates what's called a positive airflow or a stacking effect that allows that air to drive through and out. Now, ideally, the underlay is also going to be slit or terminated at the ridge, and that will improve roof ventilation, and that's well cited in the Metal Roofing Manufacturers Code of Practice as a guideline there. What happens if you don't have eaves vent? What if you just ventilate that ridge? Well, what will happen is that the pressure differential is going to draw that internal moisture through the ceiling lining into the roof space to take it out at the ridge. So if you don't bring drier air through at the eaves, you're going to bring more moist air through from the internal living environment, and then you're going to create even a more warm roof. So you need both areas there. One project I went to see was a villa re-roof, so an old traditional villa, and they had a lot of condensation in the roof space. Now, they just lifted the roof and replaced the roof, no consideration to any other changes in the house. The key factors were open light fittings throughout the house, basically making an easy access pathway for the internal environment to be the same as the roof environment. But the other key change was they changed the bathroom in that villa to a beautiful double-headed open shower, producing an awful lot of moisture with these open light fittings and an old fan on the window. And so the area above the bathroom in the roof was the area that they said was the worst for condensation. Quite simply, the roof area was getting too much moisture from the occupant generation below, and the roofer wasn't aware what's happening below. He's just trying to deal with what's in the roof, but it's been heavily impacted by occupant behavior and design below. So, what can we do when we're designing to make sure our roof is going to perform well? Now, in a generic way, we're going to take it for granted that the consideration has been made for solar lines, orientation, and so on, that the sun is going to get on this roof and it's going to be able to heat up and dry out. We're talking cold roof design. But we need to look at a clear ventilation pathway from the eaves to the ridge. So we have soffit vents, over fascia vents, behind fascia vents, purlins that are set back to allow ventilation pathways at the eaves. We need that air in at the eaves. We sometimes have issues where bulk fiber insulation can block the ventilation pathway at the eaves. And while a heeled truss is expensive, the baffle product that you see in the image on the right is very commonly accepted on the market. It just holds that bulk fiber insulation down and creates a ventilation pathway. Do make sure you don't block the top of it with a purlin. Install it as per the manufacturer's specifications. We would always recommend at Thermocraft that the underlay is slit or terminated at the ridge in line with the code of practice to allow a good pathway for the internal roof moisture to move out. We're very happy to go to bat with council. If you have a council that's less than fond of signing that off, we'll have that conversation and get a written documentation for you from council supporting that. Most councils are very supportive. Use a vented soft edge or vented ridge to ensure that the air can cleanly get out of that roof space easily. And of course, control the air sealing leakage, manage your occupant behavior and moisture generation as we've discussed. A skillion roof design, of course, is a more risky design. There's much less air volume within the space, maybe only 3 meters square of air volume. So if I had, in a sense, a bucket of water vapor in a truss roof, I've got much more air volume to spread that bucket across before I get to 100% relative humidity. In a skillion roof, that bucket of water can completely overwhelm that skillion roof in a very short period of time. So the key focus I need to have for a skillion roof is managing moisture ingress into that skillion roof and getting that moist air taken out as quickly as possible, and then I will have a functional skillion roof. Where do we have issues? We have issues where the insulation might completely fill the rafter and the purlins just sit across the rafter and there's no clear ventilation space going up the roof. So for a skillion, you really need a good amount of ventilation coming into the roof at the eaves. If I go back to the British standard, BS 5250, or the Australian standard, they're both saying 25,000 millimeters square as ventilation coming in. So a high level of ventilation coming in at the eaves, and then that air needs to get out at the ridge as well. You could also apply this concept to a low pitch truss roof, which might go to a parapet. That that apron at the top there needs to be able to clearly allow ventilation out, and it needs to function very well because we're only doing it on one side of the building. We probably also need to be very aware of any shade lines from that parapet affecting the function of the roof, creating effectively a cold spot where that area of the roof can't heat up and it stays in a liquid state. So you'll see there in this image, I've got some products on the bottom right. I've got a castellated timber batten and I've got a plastic batten. So I've said to you, you need to have ventilation. Now, in the drawing that we have on screen here, the insulation is not completely filling the rafter. So that airflow is able to move under the purlin and then go out through the ridge. That's the minimal amount. The minimal amount is 20 mils of ventilation space between the insulation and the underlay. That's the minimum amount of ventilation space, but a skillion would really benefit from more ventilation space. A plastic batten that goes over the purlin, a Cavibat, a VB20, there's plenty of products, a castellated timber, will all allow more ventilation to go over the purlin and under the purlin, creating a better drive to reduce that moisture load. So what are some of the design considerations? Well, I want you to think about the ventilation pathway think about how the soffit or an over fascia, behind fascia vent can be installed in your skillion roof to bring that air in cleanly and of a good volume to create a stack flow up the roof. Obviously, we're talking about ridge vents or vented aprons, very important. Those low pitched truss roofs are the ones that we commonly see mold issues in because they're not adequately ventilated. This is definitely a type of roof where I would consider looking at controlling the internal migration of moisture from the internal environment, vapor control barriers or layers that will prevent internal moisture migration into the skillion roof. You'll see in the image on the right, there's another little batten that's sitting above the underlay. That's sitting between the underlay and the roofing iron. Now, this is not particularly necessary in a truss roof design of a standard truss roof, but in these low skillion roofs or truss roofs, skillion where the ceiling line follows the roof line, sorry, I might find that the underlay is the same temperature as the roofing material, and because there's so much moisture in that roof space, that I'm having difficulty with that moisture condensating on the underside of the underlay because it's the coldest area. A 10 mil batten separating the underlay from the roofing material changes that temperature of the underlay. So now I can hold more moisture in a water vapor and have a better chance of getting that out of the roof before it finds an area cold enough to condensate on. And then I have to wait for the drying cycle to evaporate it and take it out of the roof. So using a 10 mil ventilated batten between the underlay and the roofing profile in a risky roof like a low pitched truss roof or a skillion roof is a good idea to assist in that condensation behavior. The other way that we can manage the the moisture risk within a low pitch truss roof is consider the type of insulation we're using. Now, a bulk fiber insulation is a very vapor open insulation. It will allow that internal moisture to come through the ceiling, through the bulk fiber, getting colder and colder as it goes. Cooltherm K7 is a phenolic board. It looks like so. It's a closed cell phenolic board, and it's used in roof insulation where we want very high R value and thin thickness. Now, take for example, if I have a re-roof of a 1970s skillion style roof, I might only have 90 mil of rafter. Quite simply, I can't achieve an effective insulation in bulk fiber at that thickness. I might be getting to R2, and then I, of course, have the roofing rafters that are reducing the R value to give me a lower construction R value. A phenolic insulation, 90 mils of K7 pitched roof board is R4.2. So even though I have some reduction in product R value or construction R value due to the rafters creating a thermal bridge, allowing heat out of that building, I'm still creating a very effective thermal performance for my client in that re-roof. And because this product is a low water vapor transmission product, I'm also controlling the amount of moisture that can come through from my internal space and come through into the roof space. So I'm helping prevent internal moisture migration. I'm giving more thermal comfort to my client, and I'm maintaining the same roof height and structure, which is really exciting. A case study on this. We re-roofed a project with Kainga ore using Cooltherm K7. The occupants remained in the home. The re-roof was completed in the day, so very good for a retrofit project. You can see here, the original roof did not have insulation in it, and a repitch to be able to put glass fiber, for example, or polyester in it was going to cost approximately $40,000. So the roof was removed and we were left with the old bituminous paper that was removed and the roof cleaned back to the sarking material. The Cooltherm K7 was laid upon the roof, and you can see here they've used spray paint to mark out the electrical cables and how they've done this. And we just use a 50 mil of K7. That's an R2.35 product value. Then we installed a counterbatten system over the top and laid CoverTech 407 roof underlay. CoverTech 407 is our thickest and most absorbent underlay. For use in a low pitch truss or a skillion roof is ideal because it will have the highest amount of buffer, if you like, towards absorbing condensation until that roof is able to get to a state of drying out again. So I would always recommend using a premium underlay for low pitch skillion or truss roofs to give you the buffer for condensation management because they're at such risk. So here the counterbatten system gives a clear ventilation pathway up the roof. It protects the insulation from crushing during walking, and the roof gets laid over there. And it's done. And so it's all done in the day with no interference to the occupant behavior below. When we did a thermal performance calculation for this is what my team does. We do these free of charge with Kingspan products and dew point analysis. You'll see here that we ended up with a construction R value of 2.97. A construction R value is when we consider the insulation and the other components in the build and we build it up. So for 50 mils of cool therm, we've got a really well-performing roof. It's quite exciting. Let's talk about walls and mold in the walls. Kingspan actually has done a woofie model looking at various wall constructions to explore mold growth risk, and we looked at continuous insulation using cool therm and more conventional products as well. We were very interested to see where mold might build within these constructions and how water vapor might move through and create mold issues. Now, we looked at Auckland and Dunedin to get a couple of different varieties. One of the products that we found was most effective was the Cooltherm K17. Now, this is phenolic insulation, so vapor retardant, pre-bonded with jib plasterboard. This is installed to the inside of the frame, giving you basically a tufa, plasterboard and insulation on the inside of the frame. Now, though the frame is still cold, it's outside of the insulated structure, this product will lower the relative humidity within the frame, and as a result, it reduces the risk of mold growth within the frame, even though that frame is on the outside of the insulation. Now, it's important to note that different wall constructions will produce different mold risk growth profiles, and so we encourage you to have a cup of tea, look at the QR code and read through this and understand how these wall configurations will perform and how they could be applied to your model to reduce your mold growth risk. What we also have done recently is explored K17 for bracing. So this is a 35 mil K17 insulated plasterboard. It's got a product R value of 1.15 and it now has bracing units. So in the image on the left where we might have a steel framed home that's actually got thermal bridging coming through the plasterboard from the steel frame, it's called ghosting when it looks like that. The K17 insulated plasterboard can simply be applied directly onto that original plasterboard, creating a thermal mitigation for the bridging, giving comfort and value, and a nice new interior lining material. In the image on the right, where there's mold in the plasterboard, that plasterboard will need to be removed before the K17 is added on. Now, the advantage there, as we saw in the previous slide with regard to the woofie modeling, we're now going to create less water vapor able to move through the K17 insulated plasterboard into the frame and reduce the risk of mold. So there is a really good solution there as well, helping with that and adding bracing requirements as well. On my last slide today, I'm going to talk about other ways we might manage humidity. And we often see the internal humid environments such as swimming pools, gymnasiums, and even bathrooms, creating issues within the build where we have a lot of humidity being created in a room and it's migrating through ceiling structures into the roof or the wall construction. The classroom that we saw before is a classic example. We have a product in our suite called Trolltech. It's a wood fiber acoustic board. It's a Group 1S rating. It really manages internal humidity well, taking up to 98% humidity, making it ideal for a swimming pool application. But it's very robust and it's very highly durable as well. So it often gets used in gymnasiums as well because it is very robust, very low maintenance. This product is very easy to install to control both the sound reverberation within those spaces, but to manage the moisture. And in use with a vapor control layer, this is our self-adhesive KVAP product. It can simply be installed with the Trolltech, the vapor control layer, and then the insulation going above it to the external envelope. That creates, in simplistic terms, a very vapor controlled room, and in these instances these rooms would be mechanically ventilated. We're laughing in the office because I intend to do this to my bathroom ceiling. Take away all the damaged paint and plaster, apply the self-adhesive vapor control layer and put Trolltech in there, and I'm very sure I'm going to sound much better when I'm singing in my bathroom, and I'll never have to paint and plaster my ceiling again, so I'm very excited about that. We'd love to talk to you about how you can do some of these designs, methods, and please just contact us at Technical and we'll be more specific. So in summary today, condensation is a natural phenomenon in our building. Our building materials are capable of withstanding repeated short-term episodes of wetness, and they will dry out given the correct conditions. Maintaining internal moisture levels is key to creating a healthy home or commercial project. We need to make sure we're not putting excessive amounts of moisture into our build, and we're able to get rid of the moist air out of spaces in our build, such as the roof cavity that would get decayed and destroyed by too much moisture. So we need effective airflow resistance between the ceiling and other structures connected to the roof. We need to ventilate the roof, as we discussed, air intake at the eaves and out at the ridge. We need to consider, have we got the correct roof for our project? Is a cold roof design actually going to work in this project, or should we actually put a warm roof design in and shift that dew point to the out of the build? Now, we'd love to talk to you more about different roof designs, but we're out of time today. So if you still would like help on your project, if you want to talk about condensation in your project or how you can create a mold-free home or commercial environment, get a hold of us at technical@kingspaninsulation.co.nz, 0800 806 595. We have a specification team that will come and talk to you in your architectural practice. We have area sales managers that will come and talk to builders in your merchant chain. And for bedtime reading, all the links are tucked at the back of this presentation. Thank you very much. That's the end of me today, and you've been very patient. I'm sorry for the disturbance at the beginning. I'm going to throw open. I've got Daniel Marshall, technical lead in my team, helping me with the chat today. So let's have a look at some of the queries that we might have from Dan online. Dan, what have we got here?
Yes, we've got a couple of questions here. The first one from Richard Puller. Thank you, Richard. Why are architects still putting profiled foam on plans at ridge and eaves?
I honestly have no idea, actually. I think it's probably because historically it seemed like a really good idea, but actually what a profiled foam does, there is a specific application. It would be a highly ventilated building and you're controlling that whole space. We very rarely see those buildings built like that. So the profiled foam closure blocks the ventilation pathway up the crest and it blocks it at the top. So basically you mean that even if water vapor was able to pass through the underlay, it can't get out. If there's condensation above the underlay, it can't get out. And so you effectively kill the functionality of the roof. If you'd like to prevent vermin from getting in your roof, there's many different products, lots of vermin combs, profiled metal combs, many different ways that you can prevent vermin from getting in there, but you must have ventilation. Please don't use profiled foam closures. The birds love them. They love to pull them out. Just don't use them. I don't know why they're still doing it.
There
What
is
else
a
have we?
bulletin put out by the MRM Code of Practice recently as well, which I'll dig out and attach to the chat there. And just last, a nice thank you from Anastasia. That's our last question for today, unless there's any more coming through.
Okay, that's good. That's crazy. I see Dan's been busy putting all sorts of articles into the chat for you as well. We will send you out a recording of this presentation, but if you'd like us to come and talk more specifically, or if you want us to talk about your project, if you're a roofer and you've got a roof that's having some issues, we'd love to have a chat with you about it. You're welcome to touch base. Thank you very much for staying with us today. We look forward to seeing you on our next webinar. Thanks very much, everybody.